Hello and welcome. This is an addendum video to Columbia Basin Research's multi-part series on using Program Atlas, which stands for Active Tag Life Adjusted Survival. This addendum video introduces the new edition of the full virtual release with dead fish correction study design to the program. Atlas is a program created by Columbia Basin Research at the University of Washington School of Aquatic and Fisheries Sciences, with funding provided by Bonneville Power Administration and the U.S. Army Corps of Engineers. Program Atlas allows users to analyze the survival of migrating smolts in the Columbia River Basin using acoustic and radio tagging data. This software is also generally applicable to other release recapture studies using active tags. Active tagging technologies allow increased flexibility in designing survival studies, but also introduce the problem of tag failure. Tag failure can be the result of mechanical or battery failure and cannot be distinguished from mortality in release recapture studies. Therefore, the perceived survival estimates, the probability of a fish and tag being alive, must be adjusted for the probability of tag failure to obtain a bias-corrected survival estimate. Today in this addendum video, I'm going to show you the ins and outs of the ViRDCt ViRDCt model and its inclusion in Program Atlas. Alright, so let's fire up the program. You can see here on the splash screen that I can now choose the ViRDCt model as a selection option from version 1.8.3 onward. You can also see from the Edit menu in the main Atlas window that you can select Change Study Design to now select the ViRDCt model from within the program itself. I've loaded in a tag history file, an attribute group file, and a tag life data file, so I can show you what's different as we go through the full ViRDCt model within the program. Let's get into the nuts and bolts about what this study design actually is. The full ViRDCt study design is used to estimate the probability of dam passage using a virtual release at the dam face, a dead smolt release in the dam tail race, and two downstream detection sites, one at the tail race and one at the tailwater. For the ViRDCt study design, Program Atlas models the live and dead releases with a joint release likelihood. Here you can see a schematic of a full release dead fish correction ViRDCt release recapture model to estimate dam passage survival. The ViRDCt model utilizes a virtual release group formed at the upstream face of the dam, V1, from tag fish farther upstream, R1. A tail race detection array located 1 kilometer to 2 kilometers downstream of the dam records detections of fish from the V1 group, including those that died during dam passage and drifted far enough downstream to be detected. Dead tagged fish are released at the dam, D1, and detections of these fish on the tail race array are used to correct the bias that occurs from detecting fish from the V1 group that died during dam passage. Due to the proximity of the survival array to the dam, the ViRDCt model does not require the R2 and R3 paired releases of such designs like the Viper design, because corrections for mortality that occur beyond the tail race are not needed. A ViRDCt study uses a virtual release of live smolts in conjunction with the release of dead smolts in the dam tail race to estimate the survival of smolts through the dam. Detections from the dead release are used to adjust dam survival estimates for the possibility of detection of dead fish at receiver arrays downstream at the dam. Details are given in the appendix at B24, and the methodology is given in Harnish et al. 2020. Atlas 1.8 implements the full version of the ViRDCt model. An alternative reduced version of the ViRDCt model will be implemented in a future version of Atlas. The data for the ViRDCt study design consists of one virtual release group created at the dam face array and one release group of dead smolts in the dam tail race. The virtual release is denoted V1 and the dead release D1. By default, the first release in the capture history data file is designated as V1 and the second as D1. Any subsequent releases will not be used. Thus, if there are multiple upstream releases that make up V1, they must be configured in the define release groups dialog, as shown here. The ViRDCt model requires exactly 3 detection sites: the site that determines a virtual release, virtual site, and 2 downstream detection sites consisting of a tail race detection site and a tailwater detection site. Here you can see the status report for a full ViRDCt study. Now let's look at the tag correction report. Here we can see a tag correction report for a full ViRDCt study. Note the values circled in red for the D1 release at site A2, the tailwater array. It is sometimes the case for a ViRDCt study that there are too few detections of the dead release at the tailwater array to estimate the tag life correction variance. These cases are indicated by the message below the table corresponding to the dagger symbol, which states that NAs indicate insufficient data to estimate tag life correction variance. Let's look at equate parameters across releases. For the full ViRDCt study design, the only parameters that may be equated across the V1 and D1 releases are the detection probabilities in the tail race, as shown here. Now let's turn to the Constrained Parameters tab. The survival parameters for the full ViRDCt study design may be constrained by the logit function, and the capture parameters, including combined survival and capture probability in the last reach, may be fixed to 1.0. It is actually worth noting that you'll generally want to constrain parameters when they are at or extremely close to 1, as a 1.0 here will likely cause compute compute to error out as seen here. So let's click on capture here and then constrain these 1.0s as seen here. This should allow the computation to proceed as intended. If we switch to the parameter report tab, we can see the parameter report with estimates of the dam survival, release specific survival, and detection probabilities. The implication of not being able to estimate all tag life correction variances is that upon computing the parameter estimates, the parameter report will reflect variances based only on the inverse Hessian. This is the equivalent to assuming that the unestimable tag correction variances are 0.0 and results in an underestimate of the true variance for the survival and detection probability estimates. Also, the estimate full variance function will be unavailable. A warning message is included in the parameter report in this case. The closed form parameter report is unavailable for a full ViRDCt study, regardless of whether all tag correction variances are estimable. A few notes to keep in mind. The view mixing function is not applicable to the ViRDCt study design because the downstream release is extended throughout the study. The closed form parameter report is not available for the full ViRDCt study design, but you can see model estimates under modeled survival estimates on the navigation panel. Only the model estimates are available for the full ViRDCt study design. This has been an addendum video on using Program Atlas's new full ViRDCt study design model. Please note that if for any reason you are having trouble with Program Atlas and these videos are not sufficient to answering your questions, you can find the user manual at cbr.washington.edu/analysis/apps/atlas. If you're using Program Atlas and you have any questions or comments, on the same page you may give us feedback via our user satisfaction survey. We would greatly appreciate any feedback you have in helping us make future versions of this program to be more useful to our users. We hope that this video helps you get the most out of Program Atlas. Again, if you have any questions or comments in regard to Program Atlas, please fill out our survey as previously detailed. You can also contact Columbia Basin Research at web@cbr.washington.edu. Best of luck with your analyses and thank you.